Okay, welcome to the first lecture of ON1, and we are going to be talking about sets. So I'm going to start off by just showing you some symbols that you can use to construct sets, and then we will look at some examples and how to convert one type of example into another. So sets. Sets are built up using three symbols really, 2 to 3 symbols. We have, I'm going to try and do this very carefully so it looks nice. That is an open curly bracket, and that is a closed curly bracket, and then there is a comma. That's not very much, but it turns out that just with those 3 symbols, we can actually build up the natural numbers. So we can start asking ourselves about prime numbers and kickstart mathematics in that sense. And without too much more notation, we can start defining the real numbers and the complex numbers and so on. So there is a lot of power based in just those 3 symbols. Let's have an example. Let me set S to be equal to the following set. It's going to be apple and orange. That's a set. We separate the elements in the set with the comma, and the open and closed brackets tell us where the set starts and finishes. So this is an element of the set. And how do we denote an element being in a set? We do it like this. So we say that apple is a member of, so this is a new symbol, apple is a member of S. So this is belongs to. How do we say that an element is not in a set? So we could say pear is not an element of S, does not belong to. Right. The order doesn't matter, and the number of times we write something down doesn't matter. So the order and multiplicity of elements does not matter. So for example, we've got our set S, but I can write S in the same way, but just swapping the elements over. S is the same set as orange apple, and it is also the same set as apple orange apple. The fact that I've written it down a second time doesn't matter. There are still only 2 elements in that set. Right. What else do I want to say about that? Not very much. I think what I want to do now is to say how to construct sets. So these sets are in list form. So what that means is I've just listed all the elements out. I could have another set that's equal to 1, 3, 5. That would be one way of doing it. But let's see how we can construct that set out of ones that we already know about. So can construct sets with predicate form. And this is very useful if, for example, you don't want to write down if you have an infinite set you have to work with, you're not going to be able to write down all the elements in a list. So this is the way you do it. You say A is going to be equal to the set of elements X that you're after, satisfying some predicate. So don't worry what predicate means just yet, we'll be looking at that in great detail. But this is what I want, and this is what it has to satisfy. So let's see if we can construct this set A using this mechanism. So e.g. for this set here, A is going to be, I want the elements that are natural numbers. So the natural numbers I'll come to in just a second, but they are the counting numbers 1, 2, 3, 4, etc. I want the X in the natural numbers such that X is equal to 2n plus 1. I want it to be odd for some n in n, and I want X to be less than or equal to, let's say, 6. So I only have to look from the elements 1 to up to 6 and find out which ones are odd, and then I will get that list. So that is 1, 3, 5. I'll just take one more example like that. One that's defined by a quadratic equation. For B, I'm going to say let the elements Z in Z, so these are going to be the integers, such that Z squared minus 3Z plus 2 is equal to 0. Okay, so I know how to factorize this. Hopefully I'll remember from school. It factorizes as so, and from that you can see if this is going to work, I need Z to be equal to 2 or 1. So I can convert this description into list form by just saying what the solutions are here, and they're 1 and 2. So that's converting from predicate into list form. Okay, let me just give some more examples of some sets that we will use a lot. So more examples. First of all, we can always have a set with no elements in it. So the empty set is written in two possible ways. You either just give the open and closed brackets on their own, or you give this symbol. So this is a circle with a cross through it. Both of them mean the empty set. Now, one mistake that always gets made is the following. If you want to describe the empty set, then you just give one of these descriptions, but this is not the same thing. This is not the empty set. It is, in fact, the set containing the empty set. So I can just write this in the other manner, and you can see that this is not equal to this. This is a set that has no elements in it at all, but this is a set that has one element in it. What is that element? It's the empty set. So these are definitely not the same thing. So if you want the empty set, do not write this. You have to write that, or you have to write that. Okay. Because we always use these basic sets to construct other ones, let's just remind ourselves what the natural numbers are. So natural numbers start with 1, not with 0, and they go up like that. If I want to include 0, I might write zn 0, or I might write z greater than or equal to 0, but that will be the set 0, 1, 2, etc. Z is, of course, the integers. So the natural numbers would have been known by the Greeks. The integers, well, somebody had to come along and add 0. That was done by Brahmagupta, who's an Indian mathematician. And the contains all the natural numbers, but it also contains the negative numbers as well. So it goes on like that. So that should be familiar. We also have the rational numbers. So these I'm going to give in a sort of predicate form. I'm going to say that they are the fractions a over b, such that a is an integer and b is a natural number. And if I want to get rid of the duplicates, so I don't get things dividing top and bottom, I can also say that the GCD of a and b is 1. From the rational numbers, you can eventually construct, it's not very easy, but you can construct the real numbers. But for us, the real numbers are just going to be any number with a decimal expansion. So it's going to be A0 dot A1, A2, A3 going on. And A0 is going to be an integer, and the AI are going to be in the set from 0, 1 up to 9. And that's for I bigger than 0. Now that will have some duplicates in it, because it will have 0.99999, which is the same as 1.000. But we're not going to go into how to get rid of all those duplicates. There is a process called completion which deals with that. But we are also going to talk about the complex numbers, and the complex numbers are just going to be the numbers a plus ib, such that a is a real number and b is a real number. Okay, and that's all I want to say for this lecture.